theory. We're going to dive kind of into basic atomic theory, and then this chapter kind of covers atomic theory, introduction to the periodic table, and then naming. So we'll really dive into naming when we get there, which should be a total review for those of you that had me in Chem. Most of you haven't, so we'll see where we're at with naming. But I think on our pretest we were okay there, so that's where we'll go. So this is chapter 2, but we're going to lump chapter 1 and 2 together. All right, we're going to start with some basic fundamental laws of chemistry. Can anybody think of one before I even put it up here? The law of the... No, not quite. Law of the conservation of mass. Law of the conservation of mass. We learned last year in physics about the conservation of energy, right? Energy cannot be created or destroyed, but now that applies to mass. Okay, so the law of conservation of mass says that mass is not created or destroyed during ordinary chemical reactions. Okay, ordinary chemical reactions means anything we do that's not going to extreme measures, right? Even in extreme measures, we shouldn't really see any sort of loss of mass or gain of mass. But that's what the law says. In ordinary chemical reactions, we should never see a loss or a gain of mass. Yes. So this led to the law of definite proportions. Once we determined, right, people a lot smarter than me did a lot of experiments to determine the law of conservation of mass. It also led them to the conclusion that once a compound is, established, once we establish the fact that water is 2 hydrogens and 1 oxygen, right, once we establish a compound, it contains the same elements in the same proportions, regardless of the size of the sample or where the compound comes from. Okay. So essentially what that means is that any molecule of water, right, pure water, should always be H2O, right? No matter where we get the pure water from, no matter if it's 1 molecule of it or 1,000 molecules of it, it should always have the composition 2 hydrogens to 1 oxygen. Okay? The same applies to any other compound. Okay, that's the law of the definite proportions. Okay, that's the example I gave there with water. Water always has 2 hydrogen, 1 oxygen. You don't have to write down the example unless you want to. The same would also be true with carbon dioxide. What's the ratio there? If I say carbon dioxide, what's the ratio? CO2, so 1 carbon atom to 2 oxygen atoms, right? That's always the ratio of CO2. All right. They also knew that scientists can combine 2 elements in multiple ways to form multiple different compounds, right? 2 elements can combine a lot of different ways. For example, carbon and oxygen can make CO, which is carbon monoxide. It can make CO2, which is carbon dioxide, right? Those 2 things behave much, much differently, right? That is called the law of multiple proportions. Okay? So those are our 3 big atomic laws. Okay? Those are our 3 big atomic laws. Law of conservation of mass, law of definite proportions, and law of multiple proportions. Okay? This is something that I think we should know, but I want to say it again. When we form compounds, it's whole atoms that chemically combine. If I know that water is twice the amount of hydrogen as oxygen, I can't do this. Right? That's not a thing. The ratio is still the same, twice as much hydrogen as oxygen, but we have to combine our atoms in whole number ratios. So that's super important. I don't think that's something that anyone in here was confused about, but I wanted to make sure we mentioned it. one of the first atomic theories that was really proposed. There's been some discoveries and changes to that atomic theory since then, but I want to talk about Dalton was the first one to really come up with an atomic theory. John Dalton was his name. And he said each element is made up of tiny particles called atoms. And he was really under the understanding that atoms were as small as they get. Right? Nothing is smaller than an atom. Do we know something different of that to be true today?
Yes.
Right. What is it that makes up atoms themselves? What'd you call them? What'd you call them? Neutrons. Okay, so that was one kind of difference from what Dalton said. He said atoms of a given element are identical, and atoms of different elements are different. Okay, that should make sense, but the first part of that has been proven wrong. Atoms of a given element are identical. That is not true, and we'll look at why that's not true here in a minute. Okay, what he's saying there is that every oxygen atom is identical. Every hydrogen atom is identical, but hydrogen and oxygen are not identical to each other. Okay, so that's half true. Third point he said is that chemical compounds are formed when atoms combine. A given compound always has the same relative numbers and types of atoms. That is true, right? That's the same as the law of... No. Definite proportions. Good. The law of definite proportions says when compounds make a compound, it's the same every time. Okay. Last part of his, sorry, I don't know why that's on there. Chemical reactions involve reorganization. They change the way they're bound together, but the atoms themselves don't change, which is true. Okay, you don't have to write down the chemical reaction I wrote down, but I want you to look at it. Chemical reactions involve the reorganization of atoms, and so it means they might rearrange the way that they're bonded, but they're not coming or going, right? And what law does that support? They're not losing or gaining mass. Which one is it? The law of conservation of mass. Okay, so if we look at this chemical reaction, we start the left side with 2 lithiums. We've got 2 lithiums on the right. A sulfate, a magnesium, 2 chlorine, 2 chlorine. Right? That's the law of conservation of mass, and that's what he said. When we react elements, we're not changing the atom itself. We're just changing the way it's arranged. We're changing who it's bonded with, but we're not changing the atom itself. So that was important, and that's still true. Okay, so there's a couple different things from his theory that have changed or have been just proven false, basically. Okay, so we'll talk about a couple of those changes here. We'll talk about it here in a second. But we know that there is a central part of the atom that contains a positive charge. Right? Anyone remember who discovered the nucleus? Starts with an R. Yeah, good. The gold foil experiment. Rutherford. Nice. Rutherford discovered the neutron. And we'll look at the experiment he did to discover that nucleus here in a sec. I said neutron, I meant nucleus. Okay. He found out that there's a positively charged central part of our atom. And he also knew that there has to be mass found somewhere in the atom as well, so we put it in the nucleus, and obviously that's true. Okay, but today we know that atoms are not the smallest thing. Protons, neutrons, electrons are smaller. Okay, so here is the experiment that Rutherford conducted that discovered the nucleus. Okay, so let's review this here. He shot out these particles that are called alpha particles. Alpha particles are positively charged. That's really important. They're positively charged. They ran through this foil. His expectation was that particles would run straight through the foil. No problem. right? And most of them did, based on this depiction of it. But what happens to the 3 that you see that have been deflected? Where did they go? Right. They went somewhere else. They were deflected. They didn't go straight through. And so if a positively charged atom was deflected, what does that mean it had to have run into? Something positive, right? Positive and negative attract, positive and positive repel. That's the word I'm thinking of. Deflect, whatever we're looking at here, okay? But they're going to repel. And so that means that these positively charged particles had to run into something positive. Okay? And so this was the Rutherford model that came from that. Here's what actually happened, right? He discovered and he kind of concluded from that experiment that there's got to be some dense region in the middle of an atom that has a positive charge. He called it the nucleus, right? He then went on to elaborate from that and say the rest of the atom is empty space, right? Electrons are so small, the atom mostly contains empty space. So we've got a nucleus and a bunch of empty space, and this is the model he came up with, called the Rutherford model, or also called the planetary model, right? Because it gives us a vision of planets orbiting, different things, but this is essentially the Rutherford model. His idea was that there was 1 electron per orbit, right? And so even if we've got this electron orbiting, this is still all empty space, right? We don't see the lines there if the electron is not in that part of the orbit. So see how much of the atom is truly made up of empty space? Right? So we see a lot of empty space there. So for it to hit the nucleus, it had to have hit a pretty densely populated region. All right, questions about that model? All right. Second thing we know is that atoms of the same element can be different. Atoms of the same element. So 2 hydrogen atoms can be different. 2 oxygen atoms can be different. The only way they can be different is with the numbers of electrons or the numbers of neutrons. But neutrons are really the most important. If you have 2 atoms with the same numbers of okay, I shouldn't say it like that. If you have 2 atoms with different numbers of neutrons, they are called isotopes of one another. That's a really important term. Different numbers of electrons just make them ions. The different numbers of neutrons make them isotopes, and they just have a little different properties. So one would have a charge, one wouldn't. Okay, but if we've got different numbers of neutrons, then we would consider them isotopes. So we're going to look at an example of that with hydrogen here in a second. So I'm going to give you kind of a brief overview of isotopes here. Real brief overview with isotopes.
So what makes the atoms protons?
What'd you say? Oh, what makes the atom's identity is number of protons. Exactly. That can't change. Right? Hydrogen always has to have 1 proton. If it doesn't have 1 proton, then it's helium or lithium or whatever. Okay, so the only way we can change elements is if we change protons. Changing neutrons just changes them into a different isotope. So hydrogen has 3 isotopes. The most common is obviously H1, okay, called hydrogen. Deuterium is H2. That's where we have hydrogen with an atomic mass of 2. And then H3 is called tritium. And that's where we have hydrogen that has an atomic mass of 3.
That's not on the periodic.
No, Because deuterium and tritium are extremely rare. Extremely rare. Like if there's 100 hydrogen atoms, 98 are regular hydrogen. There might be 1 each of the other ones. They're rare. Okay? You can see the abundance of isotopes looking at an atomic mass on the periodic table. So go ahead and pull out your periodic table. Let's look at some atomic masses. For example, let's look at oxygen. Oxygen has an atomic mass of 15.998. Is that right? Something like that? 999? Which one is it? 15.999. Okay. So what do you think oxygen's most abundant isotope probably is? What do you think the most common version of oxygen, what does it probably weigh?
16.
It probably weighs 16, right? Because look how close this average atomic mass is to 16. Right? Average atomic mass means we're taking the average mass of all of the isotopes and their abundances. We're taking like a weighted average of all the different isotopes. And so that means most likely 99% of oxygen atoms weigh 16. But there might be, 1% or even less than 1% that weighs 15. Okay, there might be less than 1% that weighs 17. Who knows? But this 15.999 is an average. It's a weighted average of all the different isotopes of oxygen. Okay? So, go ahead, sorry.
With the ones on the bottom row, in the parentheses, they're not point zero anything.
Yeah, they're not giving us an average. So they might not have stable isotopes, right? Or some of those elements at the bottom are man-made, and so they only exist for really short periods of time, so not long enough to even study isotopes. Good question. All right. Let's say real quickly that I wanted to calculate the average atomic mass. I'm going to give you the formula for that. Average atomic mass. I don't know if your book goes over this, but I want to talk about it just briefly here. Average atomic mass is what's reported as the atomic mass on the periodic table. If I wanted to calculate it, I would take the percentage of isotope A times the atomic, let's write it down, times the atomic mass of isotope A. And I would do that same thing for B. For however many isotopes I have, the percentage of isotope B times the atomic mass of isotope B. Right? And I would do that as many isotopes as I have. Okay, so I'll just throw out some example numbers here. Can you grab your calculator out for me? This is going to be made up, so we'll see how it goes. Okay, let's say that I have an isotope that's 96% abundant at 24 AMU, atomic mass unit. And let's say I've got 4% at 25 AMU. What would my average atomic mass be? Right? So what this says is that if I take out whatever element this is, which this is made up, let's say I take out 100 molecules of it. 96 of them would have a molar mass or an atomic mass of 24. 4 of them would have an atomic mass of 25. So when I calculate my weighted average, I need to convert these percentages to a decimal. 0.96 times 24 plus 0.04 times 25. And I should get an atomic mass somewhere between 24 and 25. Is that what you're getting? 24.04. Okay, so that's how those average atomic masses are calculated that are put on the periodic table. Okay? It's a weighted average of all known abundant isotopes. Okay? So it's not just an arbitrary number up there, it's an average. So let's look at chlorine's average atomic mass, 35.45. What does that tell you about chlorine?
It's a little different. Extra diverse.
Okay, it could have extra neutrons, but what does it tell you about its isotopes?
They're diverse.
Pretty diverse, or at least we've got two major ones, right? If you've got two fairly abundant isotopes, if you've got an average that's split that closely down the middle. Does that make sense? Two fairly abundant isotopes there. All right, good. That was kind of a digress from where I was going to go, but that's okay. All right. Oh gosh, we're going way back to easy stuff here. Okay, atomic number, we know this is the number of protons in an atom. I hope we know that. Yes? Atomic number is number of protons. It'll always be the whole number, right? Because you can't have a partial proton. Atomic number is protons. Atomic mass is what plus what?
Protons plus neutrons.
Good. Protons plus neutrons in the nucleus of an isotope or in the nucleus of an atom. Okay. Protons plus neutrons gives us the atomic mass or mass number. You'll very rarely hear me say mass number. Your book might. I don't. That's not how I refer to it. Okay, protons plus neutrons is atomic mass. The nuclear symbol, you'll see right here, gives us all of those things. Mass number, atomic number, and chemical symbol. On each periodic table, they're laid out a little bit differently, but what do you know is always the whole number? Atomic number is always going to be a whole number, exactly. Okay, so the nuclear symbol, I don't really need you to know how to write that down. That's not something that we're going to, use exclusively or anything, but it is something to be familiar with. If you're unsure as to how it's labeled, what do you think that the obvious guess should be? Like, if you're unsure which one's the atomic number, which one's the mass number, what could be a clue for you?
Atomic number is whole number.
Yeah, atomic number is the whole number, and it's most of the time going to be smaller than the mass number. The only exception to that is hydrogen, because hydrogen only has one proton. Okay? In every other case, the atomic number is smaller than the atomic mass. All right. Last thing here, if I wanted to determine the number of protons, neutrons, and electrons, we can use things on the periodic table. The atomic number, so let's say, for example, lithium. The atomic number of lithium is 3. Would you agree? Look on your periodic table. Atomic number is 3. Okay, so 3 tells us the number of protons, but it also tells me the number of electrons in lithium. Okay, the protons and electrons. What has to be true for that to be the number of electrons? What does the charge of our element have to be in order for it to have 3 electrons? 0, right? It's got to have a neutral charge for it to have 3 electrons. Okay? If our protons and our electrons match, our charge is neutral.
Wait, how did you figure out that you have 3 electrons?
Well, it's always the same. If it's neutral, it's the same as the atomic number. Okay, so since on the periodic table, all of those are neutral, right? All of those right now have a neutral charge, which means their protons and electrons are equal to each other, right? In order for something to have a neutral charge, your positives and your negatives have to cancel out. So if they've got 3 protons, I know it's got 3 electrons. Does that make sense?
So all of those are...
Yeah, like strontium is 38. It's got 38 electrons, right? Because if it's neutral, which all those are right now, if they're neutral, and I know it has 38 protons, that means it has to have 38 electrons. Okay, kinda? Atomic mass is protons plus neutrons. So if I want to find neutrons, I would take atomic number. Nope, atomic mass minus atomic number. Okay, I think that's something that we should know how to do already. Okay, so tell me how many neutrons are in uranium-235. Find uranium on the periodic table. 235 means that's the atomic mass I want you to use. I know. 235 minus the atomic number, which is 92. So I'm going to end up with a number of neutrons, which is 133. Is that right? No, 143. So sorry. 143.
92 electrons,
too. Okay, questions about how I came up with that? All right, how many electrons would uranium have? No, not the same as neutrons. It's the same as protons. So its atomic number is 92, which means it has 92 electrons. Okay, I guess that's all. All right, what happens if we have different numbers of electrons than protons? So what if they don't cancel out?
called ions.
They are called ions. Drew's just like piggybacking off his Chem 1 notes, okay? These are called ions. So anytime our atom has a charge, anytime our atom has a charge, it's called an ion. That's super important, okay? And anytime we have different numbers of electrons and protons, we have a charge. Okay, so ions. Anything with a positive or a negative charge is called an ion. That's super important. If you don't know that, make sure you write that down. If we have more electrons than protons, what type of charge would that lead us to? Negative. More electrons than protons. So let's say I had 9 protons and 10 electrons. Tell me first, what element would it be, and what would my charge be? Fluorine. -1. Hey, that actually worked out. That's actually its charge. Okay. Fluorine, -1. It had 9 protons, 10 electrons, so that means I've got an extra. That's how I write it, just like that. Okay, do you remember what the name of a negatively charged thing is called? Not Drew. It's not called Drew either.
A cation?
No. An anion. There you go. An anion. Negatively charged anything is called an anion.
Yeah, and the positive ones are cations.
There you go. If it has less electrons than protons, they're called a cation because they're positive.
Cats make people happy.
Right? Positive. Cats make people happy.
I don't like
Disagree. I'm just kidding. Okay.
If you don't like,
The other way I remember this is cation has a positive charge right in the, right in there. Okay, or you can do the cat thing, right? They're positive, like that. Okay. That's how somebody taught it to me one time. They're positive. Okay. So what if I had lithium with 1 less electron? What would that look like? Lithium with 1 electron. Blah, blah, blah. Li plus, right? If it's a 1, I don't put the number. The plus just means it's a 1. Okay, and then what if I had oxygen with 2 more electrons than protons? O, -2. Good. Oh, I don't know why I'm writing it. I have it on there. Okay. O, -2. So questions about charges there? Feel fine with that? Okay, good. I know this is all kind of review, but I wanted to get there. All right, that's where I want to stop for today.